Hello and welcome to this revision session for Paper 2 in AQA A-Level Physics. So in today's revision session we're going to look at how to answer examination questions on A-Level Physics Paper 2. So if we've been successful in this revision session we should be able to answer A-Level Physics examination style questions, assess our understanding on A-Level Physics and understand what topics we need to improve upon for A-Level Physics. So how should you be carrying out this revision session? When completing your work in this revision session, divide your piece of paper into two sections. Make the section on the left hand side larger than the right hand side, and in this left hand side section write down your working out and your answers to the question in the revision session. When you're doing this, make sure to write your answers in full sentences and show your full working out. Whilst in the right hand side, write down any piece of information which you find useful or any hints and tips on answering questions from this revision session, and after the revision session write up these notes into a revision sheet for you to use independently. So how should you be revising A-Level Physics? So first step is to learn the key facts. So use revision guides, class workbooks, student prep notes and textbooks to learn key ideas of the course, which may include writing out notes yourself or making mind maps. The second step should be to test yourself. So use that Caboodle, Seneca, your own knowledge checkers to quickly test your own knowledge, and you may wish to do this with your own cue cards. Then the third step is to practice exam style questions. So use exam prep books, homework books, supervised study books, additional workbooks to answer exam questions and mark your own work, and you may wish to download your own examination past papers to do this. So the three steps of learning the key facts, testing yourself and practicing exam style questions are how you should be revising for your A-Level Physics. So let's now have a look at some questions on Physics Paper 2. So the first topic we're going to look at is gravitational fields. So the first question says comets are balls of rock and ice. Figure 12 shows a comet in an elliptical orbit around the Sun. The comet is closest to the Sun at point P. Table 1 shows the data for the comet at P. Show that the gravitational force of the Sun on the comet at P is approximately 3.9 times 10 to the 12 newtons. Then secondly, explain how the gravitational force and the data in Table 1 show that the comet is not in a circular orbit around the Sun. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this first question? Well, it's only 1 mark, so you see it's a very straightforward calculation. And we know that the equation to work out the gravitational force between two bodies is F equals Gm1 m2 over r squared. You then check all your values. Now you'll notice as well that the mass of the Sun is given to you in the equation book for the exam. Pop all the numbers in and you should get 3.88 times 10 to the 12 newtons. Now the second one is asking for you to comment if it's in a circular orbit or not. Now you've already done a topic on circular motion for paper 1, and you know the standard equation to work out the centripetal force for any object going in a circle. So you can have either F equals m omega squared r or F equals mv squared over r. Now you'll notice that table 1 gives you these, so you should be using the equation F equals mv squared over r. Work it out and you should indicate that the two forces are not the same, so therefore that tells us that the gravitational force is not acting as a centripetal force, so therefore it's not in a circular orbit. The next question says, the orbital period t of an object orbiting the Sun at a mean orbital radius r is approximately given by t squared equals kr cubed. Now the mean orbital radius of the comet is 18 re, where re is the mean orbital radius of the Earth. Estimate in years the orbital period t of the comet. Then the total energy of the comet is the sum of its kinetic energy and its gravitational potential energy. Show that the total energy of the comet at P is approximately minus 6 times 10 to the 21 joules. Then calculations for a different comet show that has a total energy of plus 6 times 10 to the 21 joules at its closest point to the Sun. A student suggests that the comet will not remain in orbit around the Sun. Discuss whether this suggestion is correct. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this first question? Well, as you know, you've got a constant there, so what you can do is remove the constant but say t squared equals r cubed for the comet and t squared equals r cubed for the Earth, and you can ratio them, and you can say t squared of the Earth over t squared of the comet is equal to r cubed of the Earth over r cubed of the comet. Now you have all those values because you know that the time in years for the Earth is 1, and because you using a ratio. You do not need to convert it into seconds. You know what the radius, or so the distance between the Earth and the Sun is, the radius of the Earth's orbit, because it's given to you in the equation book. And you also know the distance between the Sun and the comet. So with that, you can work out your value for time, t, and it is 76 years. Now in this next question, you've always got to remember that the total energy of a comet is its kinetic energy plus its gravitational potential energy. So you can work out the kinetic energy with a half mv squared, and the gravitational potential energy is minus gm1 m2 over r squared. Firstly, you can't use mg delta h because g is changing over the distances, so you can't use that. And remember, it's got to be a negative value because potential is considered to be a negative, as we'll get into in the next question. So you add the two, you work each one out, you add the two values together, and you should get approximately minus 6 times 10 to the 21 joules. Now, the next question, it's going to indicate that the comet will not remain in orbit around the Sun. Now, why is that? Well, like we said before, we always have gravitational potential energy as a negative value. The reason why that is the case is because we say that the gravitational potential energy at infinity, which is outside of the gravitational field, anywhere outside the field, is equal to 0. So this is telling us that if you have to have 0 energy, for gravitational potential energy to be outside the field, it has to be at 0. So if it's at plus 6 times 10 to the 21, it's above 0. So therefore it has more than enough energy to reach infinity and to escape the gravitational field, so it will not be in orbit around the object. The next question says, show that the total energy E of a satellite orbiting the moon is given by the equation E equals minus gmm over 2r, where small m is the mass of the satellite and big M is the mass of the moon and r is the orbital radius of the satellite. Then explain the significance of the negative sign in the equation before. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? Well, once again, you've got to indicate that the total energy of an orbiting body is the gravitational potential energy and the kinetic energy. Now again, remember that the gravitational potential is a negative value, so you would have a half mv squared minus gmm over r squared. Now what you can then do is you can also rearrange this to equate the two, because one's a negative. So what you can therefore do is then rearrange your equation to have kinetic energy is a half mv squared, and it also equals gmm over r squared. So therefore we can just simplify it and say the kinetic energy is g big M small m over 2r. You can then add the gravitational potential energy to get the equation out as shown above. Now, what's the importance about the negative sign? Well, it's the idea that the satellite needs energy to get to infinity, and we set infinity to be 0. So if it's inside the gravitational field, if it's orbiting the body, it must have an energy less than 0. So it must be a minus. So remember again that the bound system, when it's in an orbit around a object, when it's in the gravitational field, it must have a negative value because it is attracted to another object. Or you could just talk about in terms of total kinetic energy, that the idea that the kinetic energy is going to be less than the negative gravitational potential energy. The next question says, the satellite has a mass of 1 times 10 to the 3 kilograms and orbits the moon in a circular orbit. The mass of the moon is 7.3 times 10 to the 22 kilograms. Determine the orbital speed of the satellite when the orbital radius is 1.95 times 10 to the 3 kilometers. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? So what you've got to do is you've got to be aware of how you can work out orbital speed. Now you can work out the orbital speed by equating the equations of the centripetal force, okay, to the gravitational force and make V the subject, or you could just memorize the equation, which is V equals the square root of gm over r. Now remember, the escape velocity is square root of 2gm over r, so don't get those confused. You know the gravitational constant is given to you on the equation sheet. You've got big M, which is the mass of the object producing the gravitational field, which in this instance is the moon. You then divide it by the distance between the center of mass of the moon and the center of mass of the satellite. Remember, they give you that value in kilometers, so you convert that into meters by putting that times 10 to the 3 again, so it'll be 1.95 times 10 to the 6. Pop all the values in and you get 1.58 times 10 to the 3. The next question says the satellite's thrusters exert a force in the direction opposite to its direction of motion as shown in figure 5. This causes the radius of the orbit to decrease. Explain with reference to energy why the use of thrusters reduces the radius of the orbit, and then calculate the work done by the thrusters in reducing the radius of the satellite's orbit. Assume that the final orbit of the satellite is circular. So pause the video now, then unpause the video when you want to go through your answers. Right, so in answering this question you've got to pay very close attention. It says with reference to energy, so you can't be discussing about forces, because even if it's correct you won't get the full marks. So it's the idea that the thrust is in the opposite motion is opposite to the motion, so therefore work is being done on the object to reduce its gravitational potential energy. We then know from the gravitational potential energy that the value, that radius is in there, because it's minus gmm over r, so therefore it tells us that the thrusters will reduce the radius of the orbit. Now how do we then work out the work done? Well, we work out the difference in the total energy by doing the equation we had before, which gave us the total energy, which was minus gmm over 2r. You work it out in both places, so you work it out with r in those different values, you then subtract one from the other. Now remember, we're minus and a minus, so we're going to be getting a plus, so it's going to be 6.7 times 10 to the 7 joules. We're now going to look at some questions regarding electrical fields. So this question says electrostatic precipitators are used to remove smoke particles from the gases released by coal-fired power stations. Figure 5 shows a simplified electrostatic precipitator. A metal rod of radius A is placed along the vertical axis of a hollow metal cylinder of radius B. Point X is halfway between the rod and the cylinder wall. The rod and the cylinder are connected to a high voltage supply to create an electrical field inside the cylinder. The electrical field strength E is horizontal inside the cylinder. Gases containing smoke particles enter at the bottom of the cylinder. The smoke particles become charged and attracted to the cylinder wall. The smoke particles stick to the inside of the wall, and the gases leave at the top of the cylinder without the smoke particles. Figure 6 shows the variation of the magnitude of E with the radial distance r from the surface of the rod to the cylinder wall. The rod is at an electrical potential of minus 3.0 kilovolts and the cylinder is at 0 volts. A student suggests that potential at X is minus 1.5 kilovolts. Discuss this suggestion. So pause the video now, then unpause the video when you want to go through your answer. Now again, with these types of questions, they give you the graph in the question, so it's going to ask you to reference the graph in your answer. So it's the idea that the area between A to X is much larger than X to B, so what we're saying is it's not going to be directly proportional, it's not a straight line down, so this tells us that the electrical field is not going to be uniform. In fact, it's going to be more likely to be a radial field. So it indicates to us that the midpoint is not going to be halfway between the smallest and the largest value. It would be the case if it was a uniform field, but it wouldn't be because it's not acting as a uniform field. The next question says a smoke particle enters the cylinder near the rod. Initially it is uncharged and travels vertically with a velocity of 5.2 meters per second. Figure 7 shows the path of the smoke particle inside the cylinder. The mass of the particle is 2.7 times 10 to the minus 17 kilograms. The particle acquires a charge of minus 3.2 times 10 to the minus 19 coulombs near the rod. The particle experiences an initial horizontal acceleration of 91 meters per second squared due to the electrical field in the cylinder. Determine the magnitude of E at the point where the particle acquires the charge. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? Well, you'll notice straight away you've got a horizontal acceleration and you've got a mass. So the equation that sticks out to me is the equation F equals ma. So we can use F equals ma by multiplying 91 by 2.7 times 10 to the minus 17 kilograms. That then gives us our resultant force, and then we know that resultant force is the electrical field strength times by the charge. So as a result, we can then multiply by the charge given in the question, and we can work it out to be 7.7 times 10 to the 3 newtons per coulomb. The next question says the vertical component of the velocity of the particle remains constant at 5.2 meters per second. Assume that all of the forces on the particle are negligible except the electrostatic force. State and explain any change to the magnitude and to the direction of the acceleration of the particle as it moves along its path. Refer to figure 6 in your answer. Then calculate the speed of the particle as it reaches the cylinder wall. So pause the video now, then unpause the video when you want to go through your answer. Right, so how to answer this first question? Well, it's asking about the idea to the change of the magnitude and the direction of the particles it moves along the path. So when you're looking at figure 6, which was the graph, you've got to consider about the electrical field strength. Now, we've just looked at an equation which said F equals EQ. Now, from the graph, you'll have noticed that E gets smaller. It decreases in size, decreases in size, decreases in size, because it's most likely a radial field. So if E is decreasing in size, well, then the resultant force is decreasing in size. So therefore, a resultant force causes acceleration, so the magnitude of the acceleration decreases. Now, we'll notice that the direction of the acceleration hasn't changed. There's been no alteration to the direction of the force or to the electrical field strength's direction as such. So therefore, the electrical field's direction, sorry, not the field strength, but the field's direction. So therefore, the direction doesn't change, but the magnitude does. And so you can answer both of those points in that question. Now, the next one, you're going to have to work out the speed of the particle. Now, what you've got is, we know we've got the potential difference. How do we know that? It's from the diagram as shown, and we've got the charge from the previous question. So we know that the work done on the particle is going to be the potential difference multiplied by the charge, so 3 kilovolts or 3000 times by 3.2 times 10 to the minus 19. Now, we know the initial kinetic energy of our particle is a half mv squared, and we can work that through to be 3.6 times 10 to the minus 16 joules. You can then add the work done because it's being accelerated, so therefore it's going to gain in kinetic energy. So you add the two together to get your total kinetic energy. Then what you can do is, now you've got your total kinetic energy by adding the two values together, and then you can work out V by doing kinetic energy is a half mv squared, rearrange it, make V the value, and work out your answer that way. We're now going to look at some questions regarding capacitance. So a student uses the circuit in figure 8 to determine the capacitance of a capacitor. The capacitor is initially uncharged. The variable resistor R is set to its maximum value and the switch is closed. R is then used to keep the charging current constant while the capacitor charges. The charging current is 0.3 milliamps, and during the experiment the student gradually decreased the resistance of R to maintain a constant current of 0.38 milliamps. The reading via the voltmeter is recorded every 10 seconds for 120 seconds. The time is measured using a stopwatch. The battery has an EMF of 6 volts and a negligible internal resistance. So calculate the maximum resistance of R, explain why the resistance of R needs to be decreased to maintain a constant current, and then show that the charge on the capacitor after 120 seconds is approximately 0.046 coulombs. So pause the video now, then unpause the video when you want to go through your answer. Once again, it's very important to note that all these questions are 1 mark only, so you're going to be using quite basic equations or quite simple statements in your answer. Now, to work out resistance, we know resistance is V over I. Now we want the maximum resistance, and because we know current is a constant, it's 0.38 times 10 to the minus 3, because milli means 10 to the minus 3, we've got to use our maximum value of potential difference, which is going to be the EMF of the source, which is 6. So it's 6 over 3.8 times 10 to the minus 4, which is 1.6 times 10 to the 4. Now, in our next question, it's the idea that the potential difference across the capacitor is increasing as it's charging, because it's building up that difference in charge across the both plates. So therefore, the potential difference across the variable resistor is decreasing, so that will cause a current to go down, because you need that push, that potential difference, to push the charge across and to maintain that current. So therefore, we're going to decrease the resistance to maintain that constant current. Now, in this last one, we've been given the current and the time. So the obvious thing to work out is the charge by doing Q equals IT. We know that milli means 10 to the minus 3, so it's 3.8 times 10 to the minus 4 multiplied by 120 seconds to get 0.0456 coulombs. The next question says, figure 9 is a graph of the voltmeter readings V against time t. Determine the capacitance of the capacitor. So pause the video now, then unpause the video when you want to go through your answer. Right, so how can you answer this particular question? Well, we know that capacitance is going to be Q over V, so you can't work it out from the gradient of the line, but what you can do is you can take values from the graph. So what you can do is take a reading from the graph to obtain the value of V after 120 seconds. So you're going to get between like 5.5 and 5.7 volts from how you've read that particular graph. You can then use the equation capacitance equals Q over V, and then we'll know what our charge is because we've just worked out in the previous question, divided by our value for V, and we get 8.1 times 10 to the minus 3 farads. The next question says the student makes a new capacitor as shown in figure 10. The two square metal plates have sides of length 15 centimeters. They overlap completely and are separated by a piece of dielectric material. The dielectric material has a thickness of 3.5 millimeters and completely fills the space between the plates. The capacitance of the capacitor is 0.13 nanofarads. Calculate the relative permittivity of the dielectric material and discuss whether the student could use the experimental procedure described previously to confirm the capacitance of the 0.139 nanofarad capacitor. So pause the video now and then unpause the video when you want to go through your answer. Right, so in this first question, we should be aware that to work out the relative permittivity of the dielectric material, we've got to use the parallel plate capacitor equation, which is C equals E0 ERA over D. So you can rearrange that to make ER the subject, my apologies, by saying ER is equal to C times by D over E0 times by A. Now E0 is a constant given to you. You can work out the area by doing 15 times 10 to the minus 2 times by 15 times 10 to the minus 2 to work out your area. Remember again, you need to be converting from centimeters into meters. You can then also use the idea that the separation is 3.5 millimeters by having D is 3.5 times 10 to the minus 3 to get our answer out to be 2.3. Now you should have noticed for the question 6 that it's a nanofarad capacitor and the previous one was not a nanofarad, it was much higher capacitance. So what this tells us is that this new capacitor has a really much smaller capacitance than the previous capacitor. Now I like to visualize capacitors as holding like jugs of liquid, like jugs of water. So this particular capacitor is a much smaller jug. It can hold a lot less water, a lot less charge. Now charging a capacitor is like pouring water into a jug, so if we pour it at the same rate, it's going to fill up a lot faster, and most likely you're not going to get many measurements because the current would very quickly reach zero. It would become the capacity would be completely full of charge, okay, before you had to take your readings with every 10 seconds, so it just would not work. So the potential difference across the capacitor would reach 6 volts before you could take your readings with the stopwatch. We're now going to look at some questions regarding thermal physics. So the first question says figure 1 shows a boiling tube containing melted wax at 85 degrees Celsius. The boiling tube is in a beak with cold water. The temperature of the wax is recorded every minute for 16 minutes. Figure 2 shows the results. So estimate using figure 2 the melting point of the wax. Then the internal energy of the wax decreases at an average rate of 7.8 joules per second during the time the wax changes state. Estimate the mass of the wax in the boiling tube. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this first question? Well, you should know that you change state, so the melting point will be when you have a straight line on a temperature time graph. So you look across and the straight line is occurring between about 80.2 to 80.4 degrees Celsius. When I say straight line, I mean flat line. Now the next one is we can now use this to work out the mass of the wax in the boiling tube, because the latent heat is the amount of energy per kilogram you need to melt it in this instance. So we can say that Q equals ml, and then we can also say E equals PT. Now we know what the power is because it gives you in the question, because joules per second is power, it's a watt. So you do 7.8 times by the time it needed to melt, so you can read it off the graph where it starts to have a flat line to when it finishes having a flat line. Convert that time back into seconds from minutes, and you can work out your value for your energy, which is Q. Then you can rearrange it, say M equals Q, which you've just worked out, over L, which you've just given, and then you get an answer between 0.022 to 0.025 kilograms. The next question says, describe how the average kinetic energy and the average potential energy for the wax particles changes between 8 and 16 minutes. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this one? Well, if you think when it's going from 8 minutes to 16 minutes, it's in the process of changing state, and then it decreases its temperature. So when it's changing state, the potential energy store of the object will decrease, because the state links into the potential energy store. So because it's changing state, and in this case it is melting, so therefore we're going to a substance which has particles further spread out, so the potential energy will go down. So the potential potential energy will decrease. The kinetic energy store is not linked to this because they are completely separate stores, so that stays the same. Now the temperature links to the kinetic energy store, so when the temperature is decreasing but the state is staying the same, well then the potential energy store will not change, but the kinetic energy store will go down because the object is decreasing in temperature. We're now going to have a look at some questions regarding magnetic fields. So figure 11 shows the path the proton takes as it travels in the Earth's magnetic field. The proton moves in a helix around the magnetic field line. The radius of the path is shown in figure 11 and the proton moves with a constant speed. The magnetic flux density in this region is 1.2 times 10 to the minus 7 teslas, and the velocity of the proton has two components of constant magnitude. The component perpendicular to the mag field is 450 kilometers per second, and the component parallel to the mag field is 120 kilometers per second. So the solar wind is a stream of highly energetic particles, such as protons that flow out from the sun. So state the condition in which a charged particle moves in the magnetic field and experiences no force. The radius r is constant and calculate r. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this question? So how do you know it's experiencing no force? Well, in a magnetic field, a charged particle experiences no force if either it is stationary or it's moving parallel to the field line. So it must be, because it's moving, must be moving parallel to the field line. Now, work out the value of R. Well, straight away you know you've got B, you've got Q, and you've got V. So you can work out what the force is by doing F equals BQV. Now importantly, what value are we using for V? Well, we're not going to be using the value parallel to the magnetic field because that will not be relevant in this case. So you've got to use the perpendicular velocity, which if you can see on here is 450 kilometers per second. We don't work in kilometers per second in physics, we work in meters per second, so we convert that to 4.5 times 10 to the 5 meters per second. That allows us to work out F, and we know that it's moving in a circular path. So because we know it's moving in a circular path, as we can see here, it's moving in a helix, we can use the centripetal force equation of mv squared over r. We're linking our two topics together. We've got the mass, we've got the force, we've got the radius of the orbit, so therefore we've got the speed, so we can work out the radius of the orbit to be 3.9 times 10 to the 4 meters. The next question says, explain why the proton takes the path as shown in figure 11. Then the interaction between the solar wind and the Earth's magnetic field can cause a small change in the magnetic flux density near the Earth's surface. Explain how this small change can cause the induction of very large voltages in power transmission lines. Refer to Faraday's law in your answer. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this first question? So like we mentioned before, it's very important to note that the parallel component of the velocity is unaffected by the magnetic field because it works perpendicular to the velocity. So the magnetic force is the centripetal force, and the centripetal force will always act perpendicular to the motion of the object. So therefore the centripetal force will cause the circular motion. Now in the second question, it's so important you actually reference Faraday's law. So what is Faraday's law? It's that the EMF is directly proportional to the rate of change of magnetic flux linkage. So we must be achieving a high EMF, because it indicates that in the question of an induction of a very large voltage. So that can only be achieved by a very, very big change in the rate of flux linkage. So that happens because you've got a very large area, because we know flux linkage links into the magnetic field strength and it links into the area of the object because our power cables are so long, as indicated in the question. The next question says, describe what is necessary for a charged particle to experience a force due to its movement in a magnetic field. Then show the radius of a circular path of a charged particle in a uniform magnetic field in a vacuum is given by the equation R equals P over BQ, where P is the momentum of the particle, B is the magnetic flux density, and Q is the charge of the particle. So pause the video now, then unpause the video when you want to go through your answer. Right, for this first one, you've got to just remember this key idea, and it experiences a force when it has a component of its velocity perpendicular to the field. So it's important to note that the velocity and the magnetic field are perpendicular to each other. If it was parallel, it would experience zero force completely. Now, how do you do the second question? Well, what you do is you remember that the The magnetic force here, which is F equals BQV, is going to therefore be equating to the centripetal force because it's causing the object to move in a circular path. So we can say mv squared over r equals BQV. We can then rearrange that, make r the subject. Remember that momentum is mass times velocity, so P equals mv, and we get our answer out to be r equals P over BQ. The next question says a cloud chamber is a particle detector that produces visible tracks. The tracks form as charged particles ionize air molecules along their paths. Charged particles produce spiral tracks when the cloud chamber is placed in a uniform magnetic field. Figure 11 is a full-size image showing the track of a particle created at point X in a cloud chamber. The particle travels in a horizontal plane and the magnetic field direction is into the plane of the page. Explain why the radius of the path decreases as the particle created at X travels through the cloud chamber. So pause the video now, then unpause the video when you want to go through your answer. Right, so how to answer this particular question? So it's important to note that as it's going through the cloud chamber, it's colliding with the particles in the chamber. So therefore, it's going to lose some of its kinetic energy as it whacks into them. Now, the particle's velocity will therefore decrease, its momentum will decrease. And we've just looked at our previous equation that says R equals P over mv. So that tells us, when you work it through, not R equals P over mv, if you look at the previous question, R equals mv over bq. So R equals P over bq. So what that indicates to us is that the radius of the orbit is directly proportional to the velocity and the momentum. So therefore, if the momentum decreases and if the velocity decreases, well, therefore the radius will decrease as well, showing the path in the figure. The next question says, a gamma photon produces two particles in a pair production event in the cloud chamber. Figure 12 shows the tracks due to the pair production event. Explain what figure 12 indicates about the three particles involved in the pair production event. So pause the video now, then unpause the video when you want to go through your answer. Right, it's a very common question to link magnetic fields and particles, because that's how particles were first discovered and understood in the 1950s to 1960s. So because our particles have spirals in opposite directions, that tells us straight away that the charges of the two particles produced in the pair production event are opposite because their spirals are in opposite directions. But they must have the same momentum, so most likely the same mass and the same velocity, but just in opposite directions, because the tracks have a similar radii. So therefore we know that R equals mv over bq. So if R is the same, mv must be the same. Now finally, if you look on this picture, you'll notice that there's no track before the event takes place. Now you should remember from paper 1 that pair production is when a photon is then changed into a particle-antiparticle pair. Now that indicates to us that if there's no track beforehand, well then the photon beforehand, which must be present for a pair production event, must be very weakly ionized or very difficult to detect because there is nothing there in the chamber. There is no track. Let's now have a look at some questions on nuclear physics. So the first question says FDG is a chemical used in medicine. FDG contains the nuclide fluoride 18. Fluoride 18 has a half-life of 6.59 times 10 to the 3 seconds. First, you state what is meant by the half-life of fluorine 18. Then show that the decay constant of fluorine 18 is approximately 1.1 times 10 to the minus 4 seconds. Then a sample of FDG with an activity of 370 megabecquerels is injected into a patient. Assume that the activity of the sample is due only to fluorine 18. Calculating kilograms, the mass of fluorine 18 in the FDG sample. Then the sample of FDG was produced in 12 hours before it was used in the injection. Calculate the activity of fluorine 18 in the sample of FDG when it was produced. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first question, you've got to know what the definition of half-life is. And the half-life is the time taken for the activity or the mass or the number of radioactive nuclei in the sample to halve or decrease by 50%. Now again, this next question is 1 mark, so you know it's going to be a very simple equation. So you know that the half-life is log 2 over the decay constant, so decay constant is log 2 over the half-life, so therefore you can pop it through and your work out your answer to be 1.05 times 10 to the minus 4. Now in this next question, it's a bit more challenging. Now we know we've been given the activity, and we know activity is equal to lambda n. Now we've just in the previous question worked out lambda, the decay constant, so therefore we can work out n. Now remember, 370 becquerels for the activity is 370 times 10 to the 6, because that's what mega means. So we can then use that value to work out n, which is 3.52 times 10 to the 12. That's how many particles that you have. So therefore you can then work out, okay, the mass in total by doing the n times by the atomic mass divided by Avogadro's constant. Now you know that the mass of 1 mole of fluorine is 1.8 times 10 to the minus 2 kilograms. So if you know how many particles there are, you can then work out how many moles you've got by dividing that value by Avogadro's constant, because it is how many particles are in 1 mole. And then when you know your number of moles, you can multiply by the number on the screen, 1.8 times 10 to the minus 2 kilograms, to get your total mass to be 1.1 times 10 to the minus 13 kilograms. Now in this last question, we've got a time and we've got an activity, and we want to work out our initial activity. So we say A equals A0 e to the minus lambda t. Remember, t has to be in seconds now, so 12 hours will have to be converted into seconds by doing 12 times by 60 times by 60. And then what we can do is make A0 the subject, A0 being the activity at the start. So we can say A0 is going to equal A over e to the power minus lambda t. We've got lambda, the decay constant from the previous question. We know what our value of A is 370 times 10 to the 6. We can pop our values in and we get 3.5 times 10 to the 10 becquerels. The next question says, state and explain one practical problem in achieving fusion in reactors. The equation below describes a fusion reaction that occurs in the Sun, and table 2 shows the mass of each nuclide. Calculate in joules the energy released in this reaction. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first question, you've got to realise there are 3 problems with fusion in nuclear reactors on Earth currently. Firstly, you could indicate that it's difficult to achieve the high enough temperatures and pressures in the plasma to constantly have fusion working at a consistent rate. Secondly, you could indicate that extracting the energy from the plasma after it's being produced is a very cost-effective process. Is not a cost-effective process, sorry, and actually you don't have an energy surplus after this. You actually have an energy deficit. And then finally, the idea that neutrons are produced in this fusion process and they've got a high energy, so are likely to be ionizing, which would be an issue. Now in this next question, we want to use our equation delta E, the energy difference, the energy released, is equal to delta M, the change in mass in before and after the reaction, times by C squared. So what you do is you work out your total mass before by adding the mass of 3 helium plus 4 helium. You then find the mass of the beryllium afterwards to find the mass afterwards. You then calculate your mass difference. You then multiply it by C squared to get your energy in joules, and you should be getting 2.6 times 10 to the minus 13 joules. The next question says, uranium fuel rods used in a thermonuclear reactor contain uranium-238 and uranium-235. Table 3 gives the mass of a uranium-238 nuclide and a uranium-237 nuclide. Deduce whether a uranium-238 nucleus can decay into a uranium-237 nucleus and a neutron. Then describe how a chain reaction occurs in the uranium-235 fuel. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this first question? Well, you've got to understand that a decay process, you have to lose mass ultimately, because some mass is converted into energy. So you find the mass between the 238 uranium and then the mass of the 237 uranium plus the mass of the neutron is given to you on the equation sheet, and then you notice that the decay cannot happen because actually the 237 uranium plus a neutron has a higher mass than the uranium 238, so therefore that decay cannot take place. Now the second question is explaining how a chain reaction occurs. Now the important thing to note is you've got to be aware that a chain reaction is caused by a neutron being absorbed by a uranium nucleus and causing fission from that process. Now it's only the uranium-235 that can absorb this neutron and then cause fission, and then the fission process itself will produce more neutrons, between 2 and 3 for every nucleus, which will then go on to fission other nuclei. The next question says, state one substance that is used as a moderator in a thermal nuclear reactor. The neutrons required to produce fission in many reactors are thermal neutrons. State why they are called thermal neutrons. Then explain why the kinetic energy of the neutrons needs to be reduced for the chain reaction to occur. And neutrons lose kinetic energy by a series of collisions with nuclei of the moderator. Each neutron keeps an average of 84% of its incident kinetic energy in each collision. One neutron has an initial kinetic energy of 2 times 10 to the 6 eV. To deduce the average number of collisions the neutron makes to reduce its kinetic energy to 2.5 times 10 to the minus 2 eV. So pause the video now, then unpause the video when you want to go through your answer. Right, in the first one, it's just a fact you've got to learn. Either water or graphite. Both of those are used as moderators in nuclear power stations in the UK. Now we call these neutrons in the process thermal neutrons because they have collided with the fission products and removed energy, kinetic energy from those products. So ultimately after the collisions they're in thermal equilibrium with the fuel and the moderator because they have collided so many times they have the same amount of kinetic energy. Now why does kinetic energy need to be reduced? Well, it's the idea that we need the neutrons produced in the fission process to cause fission in other nuclei, okay, and at least more than one in each event does that. Now the idea that it will be the neutron will be accepted by the nucleus depends on its kinetic energy. So the faster neutrons are less likely to be absorbed and therefore by the uranium-235 nuclei and to therefore induce fission. So reducing the kinetic energy increases the probability of acceptance into the nucleus and fission being taken out place. Now this last question, question 6, is all about mathematics. Now when you're losing a percentage or keeping a percentage of energy in each collision, you can work it out by literally by multiplying the value you're keeping it by the number of collisions. So in this case it's 84%, so it's 0.84, so you can see we're multiplying the value by 0.84 to the power of n. So we can say the final value is equal to the initial times by the percentage kept times to the power of the number of collisions. So it's 2.5 times 10 to the minus 2 equals 2 times 10 to the 6 times by 0.84 n. We can then rearrange it, make n the subject. Remember, if you've got exponentials you can use logs when you're rearranging that to get 105 out. Now the next question says, liquid sodium is used as a coolant in some types of nuclear reactor. Table 4 gives some properties of sodium. Now calculate the energy required to heat 3.3 times 10 to the 5 kilograms of sodium from an initial temperature of 20 degrees to a final temperature of 560 degrees Celsius. And then during the operation of the reactor, radioactive cesium-137 is produced. The cesium-137 is removed from the reactor as waste which needs to be stored. Cesium-137 decays into stable barium-137 with the emission of a beta particle and gamma radiation. The half-life of cesium-137 is 30 years. Outline the problems associated with the storage of this waste. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first question you're given lots of information, but what stands out to me is that you've got the average heat capacity of the solid and the average heat capacity of the liquid and the latent heat of fusion. So it's important you have to work out the energy required to heat it up from 20 to 98 degrees, and that's going to be the average heat capacity of the solid multiplied by the mass, which we're given to be 3.3 times 10 to the 5, multiplied by the change in temperature, so 98 minus 20. That gives us that energy. We can then work out the energy when it's changing state by saying E equals ml. We've got the latent heat of fusion. Now be careful in all these values, by the way, they give you the kilojoules, so you need to convert the latent heat and all the heat capacities into joules by multiplying by 10 to the 3. So you multiply the mass by the latent heat of fusion, and then finally do the heat capacity when it's a liquid, so do MC triangle T, which is going to be from 98 to 560. And then doing it by the heat capacity of the liquid. So when you do all those values, you work them all out, you then got to add them all together because we're working out the total energy. So you work out all three and you get 3.09 times 10 to the 10, 1.98 times 10 to the 11, and 3.63 times 10 to the 10. Add them all together to get 2.65 times 10 to the 11 joules. Now in this last question, you've you will be tested or asked to know about how you can store nuclear waste. So from looking at the information given in the question, you've got to link to the idea that there's going to be high energy particles released, which could be ionizing. So you've got to think about how you can shield the radiation so it doesn't release these particles around people. So you can think of having like a shield, like a steel or lead or very thick concrete wall, and also you could have maybe possibly being in water to shield it and also to cool it. The other idea is that the half-life of cesium is 30 years, so you'll need to store it for a very long time. Now the general rule in radioactivity is to store it for at least 5 half-lives, so it's down to a very small percentage of its initial value. So you'd say you'd have to store it for at least 150 years because one half-life is 30 years. So if you've been successful and you've learned in this revision session, you should be able to answer A-level physics examination style questions for physics paper 2, assess your understanding on A-level physics and understand what topics you need to improve upon for AQA A-level physics. So thank you very much for watching this revision session on paper 2 for AQA A-level physics. Thank you very much and have a lovely day.